Let's not continue the songs. Good morning from New York City. It's Thursday, March 21. It's 1:33 a.m. Thank you for joining me here so early in the morning, the midnight stream. OBS says I have a chat, but I don't see the chat. In other case, nope, that was a typo. 0 now. Yeah, welcome back. I think I missed the stream last night, but I'm happy to be back. Very important for me to get back on the stream. Otherwise, I feel like I'm just gonna Netflix and chill or scroll through hacker news for years and not get anywhere. So I'm really thankful for you guys for tuning in, watching these live streams, live or afterwards. It's been a real help in helping me focus and have a routine. Again, if you're new, my name is Kashfi. Kashfi. I'm streaming from New York City. In this stream, we're going to be reviewing through trees through educative.io's ACE the Python coding interview course. So tonight, I'm hoping to get through what trees are, what makes a tree balanced, what is a binary tree, more on complete binary tree, skewed binary trees, what is a binary search tree, implementing a binary search tree, binary search tree insertion source. As I'm reading this is like a lot of things. Okay, deletion. So this pre-order, post-order, in-order, yes. Yes, AVL insertion. Okay, so oh boy, this is not gonna be a one night thing because the challenge is all the way down here. So this might be a week thing. Okay. So tonight, let me just try to get through this first three topics and see how we go the rest of the week. What else do I have to say? If you're unfamiliar with me, what do we got? Can I see my? This is my YouTube channel. The channel started a month ago, and if you're looking to get into web development and you're starting out, freecodecamp.org is a great resource. And here you'll find my walkthroughs of the responsive web design certification. It's a great little free, not little, it's a great extensive certification program that you can access through FreeCodeCamp. And then I also have the video walkthroughs for all the JavaScript classes. So if you're looking to get started and just want to have someone code along with you, which is what I'm aiming to do, because it is a very lonely process. You know, if you have two screens, it'd be great. If you have my video on one screen and your work on the other screen, if you don't have two videos, maybe put my stuff on a phone and you code along with me. Just, do your thing. If you get stuck, look at what I did. It might help you get unstuck, or just have someone rooting along with you to get it done. Always very helpful. Alright, so like and subscribe. I really don't care about the subscribers, I guess. But what I care about is if you need help, I'm here to help you out. Leave a comment, be on the chat, whether it's some CS stuff or work stuff, or anyway, if you want a friend or something. Here for you, bud. Alright, so with that being said, let's just give you a preview. So we do 45-minute sprints, 45-minute Pomodoro sessions. So clock starts, we work through the 45 minutes, then we take a 15-minute break. After the break we come back and we repeat it. This is my flow. Other people have shorter Pomodoro sessions, but 45 minutes seems to be the right sweet spot for me. Alright, so let's get started. Let's get some fireworks. Fireworks, thumbs up. Start the clock. Introduction to trees. Oops. Introduction to trees. Introduction to trees. Oh my gosh. My bad. Where are we? Hashing. Alright, so coming up in the future, we're gonna cover hashing, heap, tree, and tree. This is the introduction. Yep, trees and their basic. I read the content out loud, so I'm sorry if you're not a loud vocal reader, but you should become one because it will help you develop some speaking skills, help you get confident in pronunciating, help you listen to yourself and pronounce different words and find those words that trip you up. I'm saying this from doing a month of these streams. It's helpful. Highly recommend it. And the more you do it, the more comfortable you get with it. Like I can already tell that after a month of doing these live streams, my tongue and lips and the vocal cords are just like have a better sense of confidence. Like this, I know what I'm talking about, so I can't. So if you're nervous, yeah, use this. Look at the camera and read things out loud. Public speaking in isolation. Alright, enough. So let's go. Introduction. Clock is ticking. Trees consist of vertices and edges that connect them. Yep, we saw that in the last one. So that one is a node, and if this is a linked list implementation of a tree. Oh wait, no, that was graphs. That was graphs. How are graphs and trees different? Oh, here we go. Unlike the linear data structures that we have studied so far, trees are hierarchical. Practice that word. Practice that word. Hierarchical. They are similar to graphs, except that a cycle cannot exist in a tree. A cycle cannot exist in a tree. They are acyclic. They are acyclic. Acyclic. Yeah. Maybe this could be my thing. Help folks, international students and first-gen immigrants like me, pronounce words. Define acyclic.
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 Acyclic. Acyclic.
Acyclic.
Huh. I always thought it was acyclic. 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 So graphs, cyclic. So trees are acyclic. In other words, there's always exactly one path between two nodes. So that's the difference between a graph and trees. Trees are acyclic. There's always exactly one path between two nodes, which is different because in graphs we saw bidirectional and was it bidirectional? One second, I should have my notes right here. Nope, did not have that. Was on the Jamboard. I just wish the Jamboard just had more, but they capped me at 20 slides. Here we go. Unidirectional and directed. Edges are bidirectional and unidirectional. And directed is just one direction. Undirected and directed. You know what I actually like? I like the Jamboard. I'll take the 20. Let's see. What are we doing? Trees. Trees, data structure. I was gonna do the lucid chart, but lucid chart is it's a little too much. I don't really need that much. Whereas Jamboard is a little too bare. Lucid is a little too much for my use case. Alright, let's go. Let's go. Trees. That's one. What's another note? Why is it all caps? Hierarchical. Hierarchical. Alright, if we're gonna do pronunciation, how about that one? Trees are hierarchical. Define.
Hierarchical.
See, even she's having she's having a hard time. Oh, nice. Uh, hierarchical.
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 Hierarchical. Trees are hierarchical. Hierarchical. Trees are hierarchical. Hierarchical. You gotta have fun with it, okay? Don't be too serious. Trees are hierarchical. They're similar to grass because a cycle cannot exist in a tree. Acyclical. Acyclical. Acyclical, right? Acyclical.
Acyclic.
Acyclical. Huh? Acyclic.
Acyclic.
Acyclic. Acyclic.
Acyclic.
Oh, look at that.
Acyclic.
Very good. This is dope.
Acyclic.
American pronunciation, British pronunciation.
Acyclic.
Oh. You can't do this to me, English.
Acyclic.
I had acyclic. And the American is acyclic.
Acyclic.
English. Hold up. What about hierarchical?
Hierarchical.
Okay.
Hierarchical.
Oh my god.
Hierarchical.
Hierarchical and then
Hierarchical.
hierarchical. Okay, Americans, British. Anyway, acyclic. We're both right. Acyclic. Acyclic. There is always exactly one path between any two nodes. That's a big deal. Alright. Trees, hierarchical, acyclic. Root node. Let's get some circles in here. Root node, a node with no parent nodes. Generally, trees don't have to have a root. However, rooted trees have one distinguished node and are largely what we'll use in this course. Rooted trees, okay. Child node. Child node, a node which is linked to an upper node. How do we want to link it? I'll use the pen. Link parent to child. Another child. Another line. Parent nodes, node that has links to one or more child nodes. Sibling nodes, nodes that share the same parent node. So these two guys are siblings, it's a parent, child, child. Ancestor nodes, nodes on a path from a node D to the root node. So, ancestor nodes. Bloop, bloop, bloop. Acyclic. So the ancestor of this node is that one. The parent of this node is this one. Siblings. Siblings. Nodes that share the same parent. Yep, these two are siblings. Siblings. Alright, so these are some words that we should add to our vocabulary. Enki. Enki was his name. Oh. Where you at, buddy? Enki, where you at? Enki. Here we go. Enki's here. We got. Create a deck. Trees, right? Trees. Add. Trees. Root node. Time to stand, but going to forego that. A node with no parent. A node with no parent nodes. Child node. Node which is linked to an upper node. Parent node. Sibling node. Nodes that share same parent node. Leaf node. A node that doesn't have a child node. The nodes on the path from a node D to the root node. The figure below shows all the terminologies described as above. Very good. Alright, let's examine this node. One is the root node, as well as the parent node to childs 2, 3, and 4. Node 3 is a parent to 6 and 7. As 2, 3, and 4 share the same parent node as 1, so they're siblings. Similarly, 6 and 7 are also siblings. Other terminologies and formulas, okay, subtree. Subtree is a good word. For a particular, let me just copy it. Actually, no, it's good to write it out. For a particular non-leaf or a non-leaf node. Collection of nodes starting from its child node. Degree of a node. Oh, that's big. Degree of a node, I'm saying it's big because I remember from my data structure class. That's something that we have to be able to quickly remember and recall. Total number of children of a node. Length of path. Depth. level of a node n, depth of a node plus 1. The length of the path from n to its deepest descendant. D-A-N-T, okay. Height of the leaf, so the height of the tree itself is the height of the root node, and the height of the leaf nodes is always 0. The height of leaf nodes is always 0. Height of the tree itself is the height of the root node. Height of the tree. So the root node has a depth of 0, height of 3. The child of the root node has a depth of 1 because we're 1 level, height of 1. Height goes from leaf to the root, so it goes that way, and depth goes from the root to the leaf. Level 2, level 3, level 4. Depth is level minus 1. Interesting. And height is, depth and height of the root node. Oh, there's a slideshow, okay. Total subtrees equals 6. Subtrees equals 6. How so? 1, 2, 3, 4, 5, 6 trees. Interesting. I'm getting the yawns. Not fun. Each node has 2 subtrees, and the left and right trees leaf nodes have no subtrees. Some tree types. Good stuff. Binary trees. Each tree type has its own particular structure and hence space-time complexity for different operations. Oh, that's very good to know. So these aren't just a bunch of random trees. These are not just a tree that just does the same thing over and over again. Each of these do different things and have different space-time and runtime complexities. But they right now emphasize space-time, okay? The n-ary tree. An n-ary tree is a rooted tree in which each node has no more than n children. It's a binary tree, binary, so it's 2. So it always has 2 children. Trinary tree would be 3 of them. And k-ary tree is how you'd probably like replace k with the number of children you want. Quiz. Can you guess what the value of n is in the figure below? What? Oh. 1, 2, 3, 4. 1, 2. Can you guess what the value of n is in the value of 4? What is? It's gotta be 4 since this one has 4. Each node has no more than n children. It's 4, right? Yes, 4 is right. Gotta be more confident. Is there anything? No, that's about it. What makes a tree balanced? Yikes. That's a good question to just have. That's the title of the slide. What makes a tree balanced? in this chapter, this is not much of a chapter, bro. We're going to study, it should be in this page, we're going to study what makes a tree balanced. Binary tree is height balanced if for each node in the tree, the difference between the height of the subtree and the left subtree is at most 1. Explain. For every node tree, the height difference. This means that any given node. I remember now, I actually had issues with this concept both in discrete structures and in data structures and algorithms. Huh. So if you're new to this and you're confused, you were never and are never alone in confusion. This definition is the foundation concept, blah blah blah. Okay. Alright, we just have to take the absolute value of height of the left subtree minus height of the right subtree. Is less than or equal to 1. Okay. Let me undo that and actually copy it. And paste absolute value. Notice to the left, look at the illustration below of a height balanced tree. Oh, here we go. It's a binary tree. Every parent has at most 2 children. Notice how the left and right subtrees all be the same height. Height 1, 2, 1, 2, 1, 2. Right, height is going from leaf to root. Depth is going from root to leaf, so 1, 2, okay. Is this tree balanced? 1, 2, 1, 2, 1, no. It is. Height of less than or equal to 1. Okay, that's true. Absolute value height of left subtree is 1, 2. Absolute right subtree is 1. 2 minus 1 equals 1. 1 is less than or equal to 1 is true. At each node, check if the difference between the height of the left and right subtree is no more than 1. At each node. Start from the leaf nodes and move towards the root node. Along with traversing a tree, compute heights of the left subtree and right subtree of each node. Okay. 1, 2, 1, 2, 1, 2, 1. Oh, here we go. Okay, so they're gonna walk us through it. Start from the lowest level. What will be the height of left and right subtree at this level? At the lowest level? I don't know. Since there are no more levels in the bottom, so height equals 0, okay. Height of the left subtree is 0, height of the right subtree is 0. Moving on to the next level. Height is 1, at this level the node has a left child but no right child. So HLT will be 1, HRT will be 0. Okay, that's how it is. What will be the height at this level? This level is 0. No children means height equals 0. Okay. Okay. Since, wait, what was the question? To root. Okay, HR, height of the left subtree is 2. Height of the right tree is 1. Okay. There's only one level at the right, so HRT is 1, yeah. Quiz is not a test or concept about checking if a tree is balanced or not. See the example below and try to solve it on a piece of paper. What am I trying to do? Test or is the tree above balanced? Wait. 1, 2, 3. 1, 2, 3. 1. 1, 2. I'm supposed to use fine. Copy paste. Copy paste. Copy paste. Copy paste. Copy paste. Copy paste. Link. 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 Four nulls, yep. Oh, marker. Cool. Height 0, height 1. 1. Height 0 here though. 1 minus 0, absolute is 1. 1 is less than or equal to 1. So it is true. Same thing here. It's balanced. 1, 2. 2. And this is still 0. 2 minus 1. 2 minus equals 2. So it's not balanced. Not balanced here either. 1, 2, 3. 1, 2, 3. 3 minus 3. 0. 0 is less than or equal to 1, which is true. Let's say yes. Ooh, no. Observe note 2. Explanation. So if I find if it's not balanced, what do I say L for? I think I meant false, but I wrote L. Like lie. So no, it's not balanced. At each node, if so, oh, so yeah, if we find a level, if we find a node where it's not balanced, then it means the whole thing's not balanced. Okay. What you said, quiz? No, it's a bad answer. I am right. Let's go. I sort of get it now. Okay. I wish there was more practice quiz questions. Next rhyme. 15 more minutes. I think this will be the last section before we take a break. is a binary tree. Binary tree is a tree in which each node has between 0 to 2 children. Yeah. Recall the left and right children of the nodes. Okay, so complete binary tree. All the levels of the tree are fully filled. Except for perhaps the last level, which can be filled from left to right. Proper binary tree, every node has 0 to 2 children. No node can have 1 children. Okay, the total number of nodes in a full binary tree of height h can be expressed as, oh boy, 2h plus 1 less than or equal to total number of nodes less than or equal to 2h plus 1 to 2 to the h plus 1 power minus 1. All of its internal nodes have 2 children. Nice. More math. There are many other advanced trees derived from the basic structure of binary tree. Okay, that's good. Good to know. Damn. Let's go back and kill some time with the old one. Tree in which each node has between 0 and 2 children. Each node has between 0 to 2 children. Types of binary trees. Complete binary tree. Full binary tree. Perfect binary tree. You know what, I think one Pomodoro session is good enough for today. Because this is going to be a long topic, and I feel already zoning out. And if you feel that way too, it's totally cool. It's just a indication that you gotta take it slower. So the goal is to become masters of these things. It's not gonna happen overnight. No matter how many videos you watch about learning something, the hard truth is learning takes time. So, alright, let's review so far. What is a tree? That might be more beneficial of our last 10 minutes. Trees consist of vertices and edges that connect them. Trees consist of vertices, which are the nodes, and edges that connect them. So I guess if we were to implement it just off the top of the head, we know that it's going to have a node, and the edges are going to be previous and next. No. The nodes would be left child and right child, right? I mean, the references to the next child would be left child, right child. Each node would have a left child and right child. Let's see. Linked list is just this and that. So now it's left and right. And that will have a left and right. This will have a left and right. That will have a left and right. This will have a left and right. How cool is that, huh? We go from just going front and back and organizing like this in a line. So now there's a hierarchy. Just by creating a reference to the next node and just it's that's pretty cool. It's like when you get to the leaf, the child, that in a way is going that way. But then there's this other connection. Like this is what we had before, but now this connection gives a level. It's crazy. See, this is good. It's good for you, for me, to learn something and reflect on it. That reflection will stick longer than, vigorously typing or memorizing a word. Draw it out. Think about it. Draw it out and think about it. Next. Wait. Another issue is that previously we've been using squares as a linked list. So oops. And it was going one direction like that. But now it's going outwards from the one node. And then this one is going outwards too. going there. Let's see what this drawing gets me. City unconventional. And that one will have another. Because they're not going to connect to each other. Because there can't be a cycle. It's cyclical. If there was a cycle, then it wouldn't be a tree. It would be a graph. So I gotta make sure of that. Look at me talking all smart. I shouldn't put it that way because it's gonna insinuate it's touching. Look at me talking all smart. Like I know my stuff or something. Bloop, bloop, bloop. Anyway, get the picture. 3 minutes. Okay. It's a good restart. What can I do in the next stream? Let's see. I still have not finished the projects. I need to do 1, 2, 3 projects, 4 projects. Still haven't finished this. I'm up to React and Redux. Yeah, it's March. I definitely want to finish this. So I did this in February. I want this to be March. And I guess I'll do these in April. Data visualization, D3. Yep. Is this 170? Alright, 68 seconds. Apologize for not making it as extensive as I promised at the beginning. But okay, some streams not gonna work out. So what we'll do is I'll come back to this tomorrow night and do another 45-minute session where we go through the next 3 sections. So that'll be Friday morning. And then Saturday will be implementing a binary search tree. Sunday will be deletion. Pre-order, post-order. Monday, what is AVL tree? What is red black tree? Tuesday, Wednesday, and then Thursday. So yeah, a week. Yeah, a week. Thank you for joining me on this stream, and I'll see you in the next stream. Take care.